we have gone straight to the edge of the event horizon and seen the point of no return. For the past 2 decades, a global collaboration of scientists around the Earth have been putting together an Earth-sized telescope with a single purpose: to image a black hole. And now we have done so.
Right, we have done something extraordinary. We've made the first picture of a black hole. If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
This is an extraordinary moment in science. It's the best verification that we have that black holes aren't just theoretical scribblings on a blackboard, musings of theoretical physicists, but real entities roaming the universe.
We all understand from a mathematical point of view that black holes exist, but to actually see something is a very visceral experience, and I think important for science and also for us to believe in it.
The black hole that we've imaged is M87. This is a behemoth. It's a black hole that's 6.5 billion times as massive as our sun. And it sits in the center of a galaxy 100 times larger than our Milky Way, which itself lives at the center of a cluster of thousands of galaxies, Virgo. They are quite literally gravity run amok, a key window into one of the least understood and yet most omnipresent forces that we are all faced with: gravity. This provides the first time that we're able to study in detail the stage that gravity sets for astronomical phenomena.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region. And you know immediately we're looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
The most striking feature in these images is the footprint of gravity. This ring-like feature with a central dark depression, the shadow of the black hole. That region where the photons that we see would have had to have come from below the horizon and are therefore absent.
It's amazing to be able to work on data which have never been obtained before. To have highest resolution observations, this is a unique time for a scientist in his or her life to work on these kind of data. So to see into an area where we didn't have any information before.
This first image doesn't represent the end of an endeavor, but rather the beginning of an era in which we have a new key window onto how gravity behaves and how it shapes our universe.
The future of this project is amazing. Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It signals the beginning of this new era in which we can study the life and times of these extraordinary objects in a way that was simply impossible before.
One of the most uplifting things for me is the team that we've built and the fact that we're doing something that people have told us was impossible. And when you, at the end of the day, do something that people tell you you can't do, it's an incredible feeling. And I think the whole team is very, very proud that we've accomplished something like this. It's not just for us, it's for everyone.
Welcome to this special panel discussion about today's exciting announcement from the Event Horizon Telescope. We're webcasting live from Perimeter Institute in Waterloo, Ontario, Canada. My name is Kate Allen, and I am the science and technology reporter for the Toronto Star, and I'm very happy to be moderating today's panel. This morning, researchers from the Event Horizon Telescope revealed that they have captured the first ever image of a black hole. This image was years, even decades, in the making. It involved 8 telescopes operating at 6 different sites on 4 continents. When combined, this created a virtual telescope the size of Earth. The scientific collaboration involved more than 200 researchers across the globe. Perimeter Institute is one of the EHT's 13 stakeholder institutions. The result of all of this hard work was today's image of the M87 black hole, an image of unprecedented resolution. The research results were published in a series of 6 papers in a special issue of the Astrophysical Journal Letters. I'm sure our panel is anxious to dig into these results and what it means, but before I introduce them, we have a short video from Avery Broderick, the Delaney Family John Archibald Wheeler Chair in Theoretical Physics here at Perimeter. Avery was a leading scientist in this collaboration and spoke during the press conference in Washington, D.C. a short time ago. We have a brief video message from him.
Good morning. It's with great excitement and pleasure that I'm speaking to you on this day. We release the very first Event Horizon Telescope images that have been a long time in coming, and it's been my great honor and privilege to participate in bringing to the world. This is a project that has spanned decades and continents, and we have been able, for the first time, to see the light on its journey, 51 million years in the making, from just outside the event horizon of the black hole M87. At Perimeter, we have the great fortune of having some of the world's greatest experts in the nature and phenomenology of black holes, and they will lead a discussion of the implications of these first historic images of the event horizon, both past, present, and future. I'm sorry I cannot be with you today, but my sincere thanks to all the panelists and everyone who is joining us at this auspicious beginning of a new era in observational black hole.
All right, let's meet our panelists. Robert Myers was appointed the director of Perimeter Institute just about 6 weeks ago, and he also holds the BMO Financial Group Isaac Newton Chair in Theoretical Physics. He initially joined Perimeter back in 2001 as one of its founding faculty members. Dr. Myers focuses primarily on gravitational aspects of string theory. He has made seminal contributions to our understanding of black hole microphysics and D-branes, a class of objects that have been important to the study of black holes. Asmina Arvanitaki is the Stavros Niarchos Foundation Aristarchos Chair in Theoretical Physics at Perimeter Institute. She is a particle physicist who specializes in designing new experiments to test fundamental theories. Dr. Arvanitaki hopes to use tools from black hole mergers to search for new insights in particle physics and string theory. Beatrice Bonga joined Perimeter Institute as a postdoctoral researcher in 2017 after completing her PhD at Pennsylvania State University. She studies general relativity, gravitational physics, and cosmology. Dr. Bonga is interested in resonance effects in black hole spacetimes, an area of study in which EHT observations are expected to play a major role. Brian McNamara is the department chair for the Physics and Astronomy Department at the University of Waterloo and the University Research Chair in Astrophysics. He is an expert in galaxy formation, galaxy clusters, and supermassive black holes. Among other things, Dr. McNamara studies black holes as a tool to understand how galaxies evolve and their impact on the formation of galaxy clusters. Thanks to all of you for being here. So, Rob, why don't we start with you? Why is today's announcement so significant?
Well, it's really the first time that we're seeing down to the scale of a real black hole. I mean, it's something that's been suspected to exist. It was something that was predicted over 100 years ago by Einstein's theory. But it's really been a tour de force, a technological triumph of this team working together to be able to resolve an object of that small size and to see the remarkable coincidence or the verification of the ideas that Einstein presented to us so many years ago. And like Avery said, it's only the first step. You know, we've seen it, but now they're poised to really study in detail the properties of the black hole and the physics, the astrophysics of what's going on in the vicinity of that object.
Aspina, what did you think when you first saw this image? And can you tell us what we're actually looking at here?
Well, what you're looking at is that a picture of the light, radio waves that are being lensed from the gravitational field around the black hole. The way that it's asymmetric has to do with the accretion and properties of the matter that's around the black hole. And it carries tons and tons of information about what the gravitational field, what the properties of the black hole are, the gravitational field, its mass. For example, now we have a precision measurement of the mass of this object called M87, which is a giant black hole. It is a 6.9 times 10 to the 9 solar mass black hole. It is located about 18 megaparsecs away from us. Just to give you an idea how strange this object is. Now, if you were to bring it closer and put it inside our galaxy, in fact, if we were to put it at the position of the star that's closer to us, Alpha Centauri, this object would be almost as big as the sun. Okay? This is a massive thing. This tells you how strange the universe is. There are things out there that go beyond our little solar system. And we can learn a lot. As Rob said, as Avery said, this is just the beginning. We can extract a lot of information, not only the validity of the theory, but also possibly discovering new particles from this image. Yeah, so I would like to continue the rest, and then we can come back to this.
Well, Beatrice, do you want to expand more on what this image and the results that were published today can do for the overall study of black holes?
Oh, it's incredibly exciting. So, I mean, so far, black holes kind of fit almost all the data that we've been recently discovering, such as, with LIGO, with the gravitational waves, and now with this image. But there are still like some other options that, these could have been produced by some weird other compact objects, maybe, well, I don't know. We consider, as theoretical physicists, we think they're weirder than black holes, but you might find them more normal. They're could be like boson stars or gravastars. They all have fancy names. And it would be really exciting to see, to get a better understanding of exactly this black hole. Is it really a black hole? What does it spin? Apparently, most likely, it's, turning and turning, and it could turn incredibly fast. In fact, so fast that, when you are sort of at the boundary of the object, things can go almost, close to the speed of light. But maybe this one is not turning. We don't really know. So learning about these things, all those properties of black holes will give us incredible insights of what these objects really are.
Great, thanks. Brian, can you tell us about how this image was captured and why it took so many years and so many telescopes?
So, why did it take 10 years? I think it's sociological, it's political, and a technical feat. So in general, when you're collecting radio waves, these are about 1 millimeter in wavelength. You need to equip a radio telescope, which is a dish very much like what you'd have in your backyard to get TV reception. You have to design receivers, and there are receivers in your car radio or in your home radio dish that are incredibly sensitive at that wavelength. So designing these receivers and building them took a long time. There are other aspects of that come into play. For example, that just the data rates are extremely high, and so you have to acquire lots of computer memory. That's sort of standard, but you need the right memory and the right quality and so on, and it's rather expensive, so you have to raise the money. It's sociological because you need expertise in a wide range of areas, and you have to get people involved, and as Shep Dolman said earlier, you have to get them to do the work. And it's political because to develop this virtual observatory, you have dishes that are spread around the world, and all of these are separate observatories with their own directors and so on, and you have to get everybody operating in concert, get everybody moving forward on the same page, and that takes a lot of time. And so when we think of science, oftentimes we think of the individual researcher working in a lab or in an office, writing equations down or making measurements. But this is really something that required an enormous team, and everybody had to be moving in the same direction. So it's a lot harder to do than simply normal measurements. And and I'll also say that why did they need 10 telescopes? You needed or n telescopes, where n is a number much greater than 1. The reason is you need to spread them around the Earth so that you're using the Earth as essentially the diameter of the telescope. And the larger the diameter, the sharper the image, and so they needed to do that. And then the more telescopes you get better coverage on the black hole, so that also sharpens the image, and it also increases your sensitivity to that radiation. So all of that comes into play. It's an enormous effort, and I'm sure that the effort was taken. I think it's paid off today, but it's not an easy thing to do. So that's why it took a decade just to develop to get the whole team moving in that direction.
Can you speak to some of the technological achievements that needed to be in place in order to produce this result? So I think Shep mentioned that there was something like 5 petabytes of data collected. I mean, where do you put 5 petabytes of data?
You put them on disks, as he said, and then you put them on planes and you move them to I think, that part of it, we can do that. I think that it's the processing part that's probably more of a technological achievement, designing the algorithms and so on to take the signals from each of these telescopes and combine them. There's so much data because you have to take data at a very high rate in time and combine all those signals. And so there are some standard algorithms around to do that. We've been doing what's known as interferometry for a very long time. But it was important to because you can get fooled simply by changes in weather. You have to get lucky, as they described before. You have to make sure that the weather is good at all the sites. And you have to make sure that all the telescopes are talking to each other and they're all synced up in time. And little mistakes can result in big changes in your imaging. And so there are standard techniques known as clean, for example, that have been used for a long time. But then the team developed other algorithms to assemble the images and compare them. And it's important to show that there are no systematic effects in the analysis and the way the data were combined that could fool you and give you an image that looks something like what you would expect. And it's oftentimes easy, when you get what you expect, it's easy to stop and say, we're there. Mm-hmm. But in fact, you can still get fooled. And I think they did a very good job of ensuring that they didn't get fooled.
Mm-hmm. And Shep mentioned that even the weather had to cooperate. So yes, it did.
Yeah, that's right. At that wavelength, the atmosphere can, just water vapor in the atmosphere can mess up your signal. And so the telescopes that were used are generally at high sites. They're at high dry sites. ALMA, for example, is at, I think it's over 15,000 feet. So it's a high dry site. There's very little water vapor between the telescope and M87. And so everything has to cooperate, and that's why they focused on just a couple of days, a couple of days of data that 5 or 6 days, I guess he mentioned, of data about a year ago. That was the perfect moment, so they got very lucky.
This question is for anyone. Why are black holes so important to understand?
Who wants to go? Okay, I can go. I'm good. Well, several reasons. It's, of course, the usual understanding the theory of general relativity, understanding better their new objects that we've recently discovered, LIGO being the most recent observation, the first of their direct observation of black holes. Now, what we're seeing now is actually black holes in a completely different environment, different mass range, different properties in principle about the way they have grown, this black hole has grown. So it tells us not only about the theory, but it also tells us a lot about astrophysics. How do we go from, we believe that all black holes have been seeded by the collapsing star. A star is about a few solar masses, let's say, or the early stars were 100 solar masses. How do we go from those small masses to that huge monster that M87 is. So that's one thing. From a particle physics perspective, we can learn a lot about particles, turns out. So there is something called black hole superradiance, which is a process where particles can affect the way spinning black holes, and as Beatrice says, we believe this one to be spinning. We believe how there are particles in our theory that can affect the properties of spinning black holes and can leave their imprint on these black holes. So how does this thing work? So imagine you have a rough cylinder that's spinning. Now take a ball and or a particle, if you wish, and scatter it tangentially from the cylinder. What you find is that if at the point of contact, at the grazing incidence, the cylinder is moving more slowly than the ball slows down due to friction. But if you spin up the cylinder, you see that the cylinder can actually give a push to the ball. So the ball can come out with higher velocity than what it came in. So this is a process where friction actually gives away energy. It doesn't take away energy. Similar things can happen now if you have a spinning cylinder and you scatter actually a wave off of it. Like an electromagnetic wave. And in fact, the first version of this process was done for a conducting cylinder. A conducting cylinder has resistance, so it has absorption, it has friction for electromagnetism. So if you scatter away from it, you see that the light, instead of, if the angular velocity of the light is smaller than the angular velocity of the cylinder, if the light is spinning more slowly than what the cylinder is spinning at, you see that the light can get boosted, can get enhanced, can get more amplitude, can get more light out. Similar thing can happen in astrophysical black holes. Now you'll tell me, okay, astrophysical black holes are huge. What types of particles, what sorts of waves can you see? Now this is where it takes us to the point that, well, when people think about particles, they think about tiny little things. Actually, that's wrong. Particles can be huge. They can be as big as the room. They can be as big as the universe. In fact, everyone is familiar with a particle that can be of cosmological sizes, and that's the photon. Radio waves. Radio waves are particles, they are photons, light, are particles called photons that are of kilometer size. Imagine a particle that is as big, light, photons are as big as the distance between uptown Waterloo and downtown Kitchener. So now there can be similarly particles that can be as big as the size of astrophysical black holes. And those effectively could cause the black hole, if they are there, in the vicinity of the black hole, there is this, through the superradiance process, that can cause the black hole to expel its spin by this continuous kind of scattering and spin it down. And then you end up with a black hole that's spun down with a huge cloud of these massive, huge particles in size that can affect the properties of the surrounding geometry. So if you had such a cloud of particles, this picture would look maybe completely different once we get a better resolution for it. So the fact that we have seen so close to where the horizon is could tell us about the presence of new particles in our theory.
Mm-hmm. So speaking of this just being the sort of the first batch of results, what are you, this is a question for anyone, what are you most excited to get next? What are you looking forward to in terms of more from the EHT?
Spin. That's the first thing.
Is
it spinning, right? Yeah. So that's the first thing. We've seen the black,
there are suggestions that it's spinning in this direction, but how much is like a really big question. Mm-hmm. And that would be really exciting. Also, to get a better understanding of what type of black holes are out there in our universe. And since, as it was mentioned in the broadcast, these black holes, they kind of play a crucial role in the formation of the galaxies, mm-hmm. right? If you have these super intense jets, they kind of slow down all the formation of new stars in that galaxy. So if you didn't have those jets, there would be a lot more stars. So having a better understanding of exactly the properties of even if we have just one single black hole that we understand really well, it may help us understand other ones, mm-hmm. and therefore have a better understanding of the history of our universe.
Mm-hmm.
So I think broadly speaking, if I think historically, black holes were a playground for mathematicians for a long time. And then there was a transition where they became a playground for the theoretical astrophysicists. And they really became a workhorse for ideas of structure formation, explaining active galactic nuclei and these jets. And now we can actually look at them. And so we can start to test those theories and try and understand, some of the ideas may be right, but some of the ideas may be wrong. And that's really the path that we're on. We're trying to understand the physical universe, and we have the theorists. We have many of them in this building, but we need the experimental, feedback to try and understand which of the theories are correct. And if we take the next step, even while the black holes are a workhorse in astrophysics, they're also a workhorse in the kind of physics that I do, which is quantum gravity, trying to unify quantum theory with general relativity. And one of the remarkable things is that they just seem to bring together so many different ideas that they've really become a watering hole, a source of new ideas where we can come together and get new insights. But again, it's a question of, there are a lot of theories, and so we need to be reined in by the experiments. And so there are people, who would predict that, you may see subtle effects due to quantum effects across the event horizon. It's unlikely, in my view, but on the other hand, now we've got a real forum where we can test those ideas. And we can come to grips with, well, if we've ruled out those theories, then what's left, and what do we have to work with?
So is there anything that wasn't revealed today that you in particular are excited to get your hands on? Any particular?
Well, I think as they go along, the resolution of that image is going to improve. As they were saying in the press conference, they're going to add more telescopes to the observations. More telescopes have already joined, but they're also shifting the frequency or the wavelength. And so the resolution of that picture is just going to continue to improve, and we'll be able to probe more and more precisely what's going on, both around the black hole to understand the astrophysics, but to take a closer and closer look towards the center and to see, are there strange effects? Could it be a boson star, or could it be some scintillation on the horizon, or some strange effects like that?
So to be more concrete, one of the exciting aspects of this particular technology is we can start to look at the launching region, where the region outside of the black hole where these jets are launched. So, when people think of black holes, they typically think of something that sucks everything in and doesn't let anything out. And of course, they don't suck. They're pretty cool. And also, things fall in. They don't get sucked in. And it is true that once matter falls behind the event horizon, it can no longer escape. But in fact, most of the matter that approaches a black hole does escape. And it turns out, even though this black hole has an event horizon the size of the solar system, it's very hard to get matter into it. And it's because most matter doesn't fall straight in, it comes in at an angle. And so then it begins to collide around the region of the black hole that you see there. And eventually it gets launched out. Now, why does it get launched out with so much power? The reason is that within that little horizon there, that black dot that you see on the screen, there's more energy bottled up in there than all of the stars in the entire galaxy of M87, and they're traveling at something like 300,000 kilometers an hour, and there's 1 trillion of them. You add up all the energy to that, and that is dwarfed by the energy that's just jammed into that hole. That energy is transferred to matter that's falling into it, and it gets shot out in these jets. These jets hit the matter surrounding it, and they control the growth of the galaxy. So this is M87, you saw the images earlier, is one of the biggest galaxies in the universe. There's nothing that prevents galaxies from growing to vastly larger sizes, and what we think is happening is that the black hole is actually regulating the growth of galaxies. And it does it in a remarkably uniform way, so that nature has found a way, for example, As matter approaches a black hole, for every atom that falls into a black hole, 700 atoms go in and create stars. And this is this beautiful fact of nature that we don't understand entirely, but we think that this thing called feedback, the energy that's released by black holes, in fact, black holes are the most efficient energy generators in the universe. That energy is imparted on the matter surrounding black holes, which is dominated by this galaxy, and it regulates the growth. And it's a remarkably complex but beautiful thing. It's got simplicity to it, and then it comes out in this beautiful magic ratio of 700 to 1. But to put it in perspective, it's as if an object the size of a marble or a grape is controlling the entire destiny of an object the size of the Earth. From a theoretical perspective, we don't understand that. From an observational perspective, nature seems to be telling us that this is so.
So we're looking at M87, but it wasn't the only target for EHT. They also looked at the black hole at the center of our galaxy. And why are we seeing M87 first? And what could we learn from the other black hole they looked at that we have not seen yet?
There's a couple of reasons for that. One is that the galaxy is really a disk, and we're sort of on the outer fringes. But to see the other black hole, Sagittarius A, it's at the center, and so you're actually looking through all of that stuff. M87 is outside, it's in another cluster, and so it's a cleaner line of sight. There are also some other technical things. In the press conference, Avery mentioned the variability of M87, or the black hole there, is on the scale of days, weeks. Mm-hmm. Whereas the variability for Sag A would be on the scale of minutes, seconds. Mm. And so it's when they're making these images, as it stands now, they're assuming that the source is not variable. And the other simple technological thing is that M87 is far enough in the northern hemisphere that they can't see it from the South Pole, and so they don't have to worry about collecting the data from the South Pole telescope, because they would have had to wait the entire winter, and so they had an extra 6 months to work on that one before Sag A.
Is there anything that we could learn from Sagittarius A that we didn't learn from M87?
Sure. One of the image that you see there didn't have to look that way, and it looks that way in part. It reflects the nature of the material falling in, and so in the case of M87, what we think is that this material falling in isn't in a very thin disk; it's in an extended, puffed-up plasma. We think that most likely that'll be true in the center of our galaxy, but we don't know the geometry and structure of that disk. It's also true that M87 is probably it's accreting matter. That is, matter is falling in at a much higher rate than Sagittarius A star. But Sag A star is also flaring a lot more rapidly than M87. So they have different properties. They may have, M87 has a jet, Sag A star doesn't. And so this will, hopefully allow us, give us better insight into the process where energy from black holes is ejected and imparted on galaxies on a galaxy scale. So I think just the different launching mechanisms and the different environments between these two holes, and these are the only ones that we'll be able to do with this technology, and that's just by virtue of the ratio of the size of the black hole in our galaxy, which is about 1 million solar masses, to the size of the black hole in M87, which is a few billion solar masses. The ratio of the distances from us to the center of our galaxy and us to M87 is about at that ratio. So they both have the images, the angular size of their event horizons are roughly the same on the sky. So these are the two golden ones we can look at. Mm-hmm. And the nice thing is that we can start looking at them, not just different objects, but looking at them over time to see how matter falls in and what happens around the black hole as matter falls in. So it's, from an astrophysical perspective, that's pretty exciting. But there aren't that many, those are the only two we're going to be able to, at least in the near future, see the event horizon. But we will be able to look at other galaxies and see stuff that's further away, thousands of times more distant than the event horizon, and then follow the ejection of material from black holes like
the two that we can see the event horizon with, two others that are too distant to see the event horizon.
So what would it take to get results from other black holes other than the two primary targets?
Well, I think they already have some.
As we were
actually,
shaking
right?
your head.
Oh, because it's like, we have a limit. It's like the angular size. Well, can you make the Earth bigger? Because right now we are.
Space,
Yes,
So
we can put our heads into it, but I don't think we will make that one happen.
Yeah.
So right now we are limited by basically how big the telescope is.
Yeah.
And we've made, and one of the great achievements of the Event Horizon Telescope is basically the Earth is a telescope. It's fancy combining data, but that's the size. And given the wavelength there is in optics, we know that there is a minimum angle we can resolve. So we work at that limit now.
But we can, don't forget, we can put telescopes in space, we can put them on the moon, we can put them on Mars.
We can make it bigger, yes.
All we need is money.
Exactly. I agree with that.
Just a little cash and we can have a telescope on Mars.
Right now, we are diffraction limited for the Earth.
right.
So the cheapest things that we could do, as correct Brian says, we have done already. But it requires just making the telescope much larger than what, so that we can see smaller things.
26 million is a good start, but we need to up that by orders of
Once you
magnitude.
go to space, yes, it's a different energy.
But I think you also, they've got a decade of work, just with these two toys.
Yeah.
They're really marvelous frameworks to study all kinds of astrophysics and answer all sorts of questions that we just don't know the answer.
Yeah, going back, Beatrice said it in the beginning very well. It's like we have a test tool. So we cannot see any stars, but we do have a star next to us, the sun. By just studying the one star that we have in our vicinity, we've managed to learn so much more about the billions and billions of stars that are inside the universe. So same way, we've seen one black hole. One black hole could be enough to tell us all sorts of things about all sorts of other black holes. The interesting thing is now that these are two black holes that have different masses as well. One is very heavy, one is somewhere in the middle of the scale, 10 to the 6 solar masses with Sagittarius, and then we have LIGO that sees solar mass black holes. So we are covering all the range. So even one data point, let's call it each observation data point, if it's good enough, can tell you tons of stuff.
So what are you all going to do with the information released today, but also the next decade of info from the EHT?
Wow.
Tell me about your plans for the next decade. What's next for all of you and your study of black holes with this new information and anything that might come out in the next few months and years? All of you. Why don't we start with
the
Rob?
truth is, for me, it's not going to affect what I do day to day, but I'm going to be waiting for surprises. I'm going to be waiting for surprises. That's what we're always waiting for.
Yeah.
Right.
I mean, it's great when, the experimental data matches our theories. That's a wonderful, confirmation that the things we're working with are correct. But on the other hand, what we're all really waiting for are the surprises. We're waiting for the results where it doesn't match or doesn't quite match, and that then presents the theorists with new puzzles, and so that's what I would be waiting for.
I want to come back to that.
Okay.
The surprises.
I was, super over the moon excited when the LIGO results came out, where they measured for the first time these gravitational waves, and I'm still super excited about that, but it's really cool because there you typically need two objects, right, going around each other. But you really only see those black holes, in their last seconds, actually even less than seconds. Here, which is pretty cool, you can actually see this object for, as long as we take measurements. So you can track what this black hole is doing over, human timescales, which is pretty exciting because it gives you a whole kind of other information. So I'm excited for, time evolution of this system. And of the one in there, the nearby one, which is probably more exciting because that one is changing more rapidly. So.
No, I know what I'm going to be doing the next few months. I'm going to be bugging Avery to show me data for the screen.
Should get a lock on his door.
It's like, I know, I've been doing this. This is pretty exciting because I've been bugging him about this stuff for a while. So getting the properties of the black hole, extracting the spins, and getting information about the nearby geometry, which they can measure very well, may not give us just surprises for general relativity, but may also give us surprise about these new particles that I mentioned. So it's actually it's a real tool, not just for understanding astrophysics. So there is things to do, but this is just the beginning. This fuzzy image is a beautiful, beautiful work of science, but it will get better, and the information that we'll get from it. So that's going to be the focus. Spin is one big parameter. If this was fastly spinning, would be pretty amazing.
So I'm still trying to figure out how an object the size of a grape controls, something would control something the size of the Earth in that ratio. So how galaxies form and why this little thing down at the center. Obviously this is a behemoth on the scale of the sun, but it's tiny compared to the size of the galaxy, and how the energy that falls in is converted into heat, which is then transferred into the surroundings and prevents stars from forming or regulates the growth of galaxies. How we get this magic 700-to-1 ratio between the mass of the black hole and the mass of the galaxy. I think that's going to keep me occupied for quite a while. And in fact, while Avery was talking, I was writing a proposal to ALMA, which is one of the telescopes they're using to try to figure this out. So we're always, there are always new angles to look at. But how these things work has fascinated me for 20 years, and it's probably going to keep me going for another 20.
So Avery mentioned that the results accorded exquisitely with the theoretical predictions so far. Is that in any way a disappointment? I realize I'm asking this in front of a room full of theorists, mostly theorists.
To me, it makes me very happy because I love GR. It's one of the most beautiful theories that I've ever, well, I think it's the most beautiful theory. But of course I'm biased. But yeah, no, I would be actually maybe even more excited if they showed something was off, right? Because we know from other considerations that GR cannot be the ultimate theory. There has to be, unification of quantum theory with gravity, which we call quantum gravity, even though we don't really know what it is. But so we know there has to be something else. So any glimpse that we can get of that something else would, of course, even be better. But in the meantime, I will smile looking at that picture and be like, wow, GR is really beautiful and true.
Yeah, it's too early to tell. This is just the first data. The data, right now we say it's kind of spinning, but in reality, the good fit is just for almost any value of spin. So there is still a lot to decipher. And we know, look, it's fair, just to go back to the GR question, we've tested general relativity in so many ways. Even before the LIGO discovery, it would have been a huge reshuffle of the entire theory if gravitational waves were not there, for example. So, we know a lot about the theory already, and in reality, we were not expecting black holes to confirm the general relativity theory. To some level, we are testing it in a different regime. So any deviations that are there, we already were not expecting it to be, you see something and blue dragons fly out. You have to dig in a bit deeper to the data to see small deviations from a theory that works so well in so many scales. We've tested Newton's law. The fact that if you put two masses together, the force between the masses goes like the inverse square of the distance. Now, we've tested this down to the millimeter scale. We've observed galaxies, the motion of galaxies, and we know that gravity also works very well up to hundreds of millions of light years of size, of length scales. So you have a theory that works so well in so many scales, you're not expecting that the first thing you see something new, that everything will be toppled over. So if there is something there, which everyone still hopes that it will be, you have to dig deep in the data, and that will take, and this is where now the hard work begins. They had to do hard work to get the experiment running, to get this image out, but for them, this is where where the hard work begins. How do you extract all the final amount of precision you can get out of the image that you see?
So we are getting to the end of our time here, so I'll ask you all for all of the non-scientists watching, you know, the general public, what do you hope they walk away today thinking about? Do you want to start, Rob?
Well, what a remarkable place. What a remarkable universe we have, and how much you know, we have to discover it in it. But it's also the idea that, you know, when you bring people together around great ideas, you know, there's the ingenuity, the energy that we can devote to projects like this just result in amazing features or pictures like this.
Yeah, I mean, Rob said it very well. It's this is a great achievement of humanity when we bring some mind together to a common goal, just like the LIGO experiment or the Large Hadron Collider experiment, where we put our minds together for something good, like finding out the origin of the universe or finding out, understanding where we're from, we can do great things. Imagine, we live in a little rock. You know, like, I think if you were to make an analogy between a grape and the galaxy, I think the Earth is even smaller than a grape. So we are in this little rock that floats through the cosmos, and we've managed to understand so much about this vast universe that surrounds us. This is just something to be at awe. It's changed, and everything that we've learned, and knowledge is so important. It changes our worldview, it changes everything. But this is a great achievement that we as humanity should be very proud of.
Thanks. Beatrice?
I can only second that.
So I hope people, and particularly young people, will be inspired by this, and will get a sense not only of the joy and wonder, but how much work there is to do. So, remember that general relativity has been tested here and it did fine. Quantum mechanics has been tested and it does fine in its own domain. But those two theories don't talk to each other. The other thing to keep in mind is the universe, 98% of the mass energy of the universe is in states that we don't understand. We call them dark energy, we call them dark matter. There are black holes, they're likely not so much dark matter, and it doesn't matter. Once it falls into a black hole, it's gone. But we don't understand that stuff. And so for the young people, I hope they're inspired to go into science and solve these problems. Nobody at this table has solved those problems. Nobody in this room has solved those problems. So we need smart people thinking with new ideas and new approaches, along the lines of the EHT to try to solve these important problems. So inspiration, I think, is the most important thing that'll come out of this.
Well, thank you so much to all of you. That's all the time we have for today. Thanks to our panelists, thanks to our audience, and thanks to our web audience.